In this session, we'll discuss about the synchronizing power. We know that when alternator is connected parallel to the bus bar or other alternators, when it is connected, it is staying in the synchronism. When there is a disturbance occurs in the alternator, still it is stay back in the synchronism because of a power, whatever calling is the synchronizing power. Then how this synchronizing power is counterbalancing the angle delta and keeping the machine under a small disturbance in the alternator stay in the synchronism when it is connected to the bus bars or other alternators in parallel. That is synchronizing power, or also it is a synchronizing the torque in the case of it is a motor. We know that a synchronous machine is synchronized to the bus bars and the loaded electrically as a generator. That we will consider a generator which is connected to parallel to the bus bars. The machine runs at a synchronous speed at any load well within its maximum steady load capability. That is, the machine is running with a synchronous speed. Then, when it is within the load condition, if it is loaded and it is running with a synchronous speed, and the load is the less than the maximum steady state capability, that is given by that is EB by XS. That we'll see. For proper operation, it is essential that the machine stay in a synchronism for a limited amplitude electrical disturbance. I told you, whenever there is a disturbance, the electrical disturbance occurs in the system or in the alternator which is connected in parallel, then it is in the synchronism with the alternator. It is because of a synchronizing power. The power angle characteristics of a cylindrical generator is drawn here. Just I will show you. That is, we know that the power angle equation is given by EB by XS sin delta. You are neglecting the resistance part here. And if you are drawing the power angle characteristics, then you are getting a power angle characteristics. Then if you have got a maximum value, steady state limit, what I am calling, is given by P max. That is nothing but EB by XS. That is the maximum, the steady state limit is EB by XS when sin delta is become 1. When sin delta is become 1. That is delta is maximum 90 degree. Okay. That is the maximum power capability of a alternator which is connected in parallel is EB by XS. Okay. If the disturbance which is less than this EB by XS, definitely the machine is still operating in parallel with the bus bars with synchronized. Then the same can be expressed as, instead of EB by XS, that can be replaced by P max sin delta, where P max is EB by XS. That is, P max is EB by XS. Now once again I am drawing the power angle characteristics with its maximum capability of EB by XS. Then we will consider now there is a disturbance in the machine. Consider the generator is operating at a load P0 at an angle T0. I will consider a point on which it is operating, the generator. Generator is operating at point P0 with the output of the P0. It is delivering the power P0. It is under steady state condition. At that particular instant, the value of the load angle is delta naught. To deliver the P naught, the corresponding value of the load angle is delta naught. It is the load is loaded with P naught. Now there is a small disturbance occurs in the system. Because of the disturbance, then momentarily the speed of the generator will reduce. If there is a reduction in the speed of the alternator, in that case there is the increase in the load angle delta. These are the dependent. If the load on the machine is increasing, in that case, momentarily the speed of the alternator will reduce. Thereby, there is an increase in the load angle delta. The same thing is given here. The electrical trajectory disturbance. Because of the disturbance, the rotor deceleration and rotor angle increases. Therefore, because of this change in the scenario, that is because of the disturbance, that is the load angle is changing to delta delta from the original value of delta naught to delta naught plus delta delta. There is change in the load angle because of the disturbance. Therefore, this result in increase in the generator output. We know that P is equal to EB by XS into sin delta. Previously it is sin EB by XS sin delta naught. Now because of the disturbance, the angle is delta naught plus delta delta. Therefore, definitely the power is increasing. That is, it is now the new power is P is equal to EB by XS sin delta naught plus delta delta. That is why it is written this result in increase in the generator output by delta P. There is small increment. That is, see here. Previously it is P naught, now it is increased because the angle is increased to delta delta. Therefore, the power is also increased by delta P. That is, delta P is increasing the power output, which causes the rotor to decelerate, countering the increase in the delta. When there is an increase in the load, there is a deceleration. Because of the deceleration, there is an increase in the delta. Therefore, delta and the speed, they are counterbalancing each other with the help of delta P. That is what we are calling as the synchronizing power. The reverse happens if the delta is negative. Similarly, if the disturbance occurs, that is some of the load is taken off from the generator immediately, in that case there is the reduction in the load from P naught to some value. In that case, angle, the speed is increasing, the delta is decreasing. This is that is the reverse happens if the delta is negative. Here the load is increased. In the case of the other way, if the load is decreased, in that case what happens? The speed is increasing momentarily. Thereby there is a reduction in angle delta. Once again it is bringing back to the original portion of P naught with the synchronous speed. The rotor settles back to delta naught in the oscillatory manner. That is what happens. It is initially operating with a stable condition with a P naught. There is a disturbance occurs. Because of the disturbance, there is a reduction in the speed of the rotor. Because of the reduction in the speed of the rotor, there is an increase in the angle delta. Because increase in the angle delta, there is a small power increment in the power delta P, that is the power output is increasing by delta P. The total output is P naught by plus delta P. Then now it is a power is increased. Therefore, then what happens? The power is more. Therefore, what happens? Because of the oscillatory manner, then this operating point is once again settled down to the P naught after the disturbance. Okay, means in the oscillatory mode, then it is finally settled at this particular point P naught. The rotor settles back to delta naught in oscillatory manner. Thus, the delta P causes by delta D is the power that brings the generator back to synchronous. Ultimately what happens? The alternator has to operate once again at P naught. When disturbance occurs, there is a change in the delta. Because of the change in the delta, there is change in the delta P. Then once again our object is to this operating point has to come down to P naught. Then it is because of this synchronizing power, that is once again the operating point is bring back to the P naught. That is the role of the synchronizing power or a synchronizing torque. Thus, delta P caused by delta is the power that brings the generator back to synchronism. The delta P is called as synchronizing power. It is called as a synchronizing power, that is play an important role bringing back the system to its stable condition. It is seen that the effectiveness of this correcting action depend on the change in the power transfer for a given change in the load angle. That is, the action of bringing back to the P naught is depending upon how much angle it is changed. If there is a large change in the angle, then the large value of the synchronizing power is required. Then one more cautionary you have to look into here, that is, if there is a large change beyond the delta is equal to 90 degree, then the system is go into the unstable condition. There is a asynchronous of the alternator which is having a large disturbance. It is seen that effectiveness of the correcting action depend upon the change in the power transfer for a given change in the load angle. A measure of effectiveness is given by the synchronizing power coefficient. Then how to find out synchronizing power? It is an incremental change in the delta P that is given by it is a rate of change of the synchronizing power, that is a rate of change of the power, that is what we are calling is the synchronizing power, that we will see in the next slide. It is defined as it is a rate at which synchronous power P varies with the load angle. That is, I told you, it is a dP by d delta is called as synchronizing power. It is also known as stiffness of the coupling, or it is also called as rigidity factor, or also called as stability factor, and is denoted by P subscript synchronous, that is P synchronous. That is, the synchronizing power is made an important role in the alternator. Whenever there is a disturbance occurs, its main role is to bringing back the system to its original operating point. That is, the ratio of delta P by delta delta is the indicative of capability of the synchronous machine to stay in the synchronism for bounded amplitude of disturbances. That is, the limit dP by d delta is known as synchronizing power coefficient, or P synchronous, or stiffness of the electromechanical coupling. These are the different names is given for a synchronizing power. Then how to find out that dP by d delta, that is from the power angle equation, that is we have got a P is equal to EB by X sin delta. Therefore, dP by d delta is nothing but EB by X is sin delta watts per electrical radians. If you are drawing the graph of both synchronizing power as well as the actual power delivered, first I will draw the power delivered, that is P is equal to EB by XS with its maximum power delivery is P max. At the same time, I am also drawing the synchronizing power versus delta curve. It looks like this. This is a P synchronous curve. Okay, that is, we know that the maximum synchronizing power we are getting when delta is equal to 0 degree, and least or a zero synchronizing power we are getting when delta is equal to 90 degree. Therefore, if any disturbance occurs, the machine should be operated between 0 to 90 degree. In the case of at this particular, if it is operating at this particular delta is equal to 0, means we are getting a maximum the synchronizing power we are getting. We are getting a maximum synchronizing power. If the disturbance is delta goes on increasing, your synchronizing power goes on decreasing. Ultimately, the synchronizing power is 0 when delta is equal to 90 degree. If the disturbance is so high that if there is a change in the angle is beyond 90 degree, and the system or the alternator loses its synchronous, that is 90. Okay. Then therefore I told you that is the system is stable as soon as when there is a change in the disturbance, that is the delta is from 0 to 90 degree, it is a stable condition. Beyond that, it is the unstable. Here afterwards the system remains the unstable, or the alternator loses its synchronism. The plot of P delta and P synchronous delta superimposed on it is drawn in the above figure. It is seen that P synchronous is equal to P max, that is P synchronous, that is synchronizing power is equal to the maximum stability limit at delta is equal to 0. It is quite evident, that is P synchronous has got a maximum at delta is equal to 0. It is 0 when delta is equal to 90. That is synchronizing power is 0 when delta is equal to 90, which is the steady state limit beyond which P synchronous become a negative, and so that the alternator loses its synchronous. Therefore, the synchronizing power is the power which is bringing the alternator under a disturbed condition back to its original operating point. That is the role of the synchronizing the power. And the synchronizing torque is obtained by merely dividing 2 pi ns by 60 to the synchronizing power, so that we will get the synchronizing torque. That is, synchronizing torque is equal to synchronizing power divided by 2 pi ns by 60, that is Newton meter per mechanical radian. This is how we have to explain, this is how we have to analyze the role of the synchronizing power keeping the system in a stable condition.